All right, let's unpack this. Building modern systems, it's less about knowing a bunch of isolated facts and more about understanding the why behind every single decision.
Hmm.
Today, we're embarking on a deep dive that's really designed to be your ultimate companion for grasping how these intricate digital worlds are built.
And crucially, why they're built that way.
Exactly, why certain architectural choices are made. Think of this as maybe your shortcut to becoming truly well-informed quickly and thoroughly.
Yeah, like a really detailed audiobook chapter, maybe.
Yeah.
Synthesizing all the good stuff.
Precisely. We're going to synthesize a stack of expert sources, research, our own insights into what we hope is a definitive guide. We'll cover, well, pretty much everything from foundational principles like the CIP theorem and the hidden complexities of networking.
Things people often gloss over.
Right. All the way to practical real-world technologies like Kafka, Redis, Elasticsearch.
The tools of the trade.
And then tie it all together with crucial patterns for building truly robust, scalable systems, our mission, to get you ready to tackle basically any system design challenge with confidence. Hashtag the foundational pillars of system design. So when we talk about something as vast as system design, whether you're prepping for an interview or just, curious about the architecture behind your favorite apps,
Right.
there's a kind of common framework that serves as a really excellent starting point. It's a structured way to approach any system, really,
Wow,
big or small.
the mental model. Yeah.
Typically, the very first step is to align on requirements. And this isn't just about what the system does, but also how well it does it.
The non-functionals. Critical.
Exactly. We often categorize these into functional requirements, which are the specific features like a user can book a ticket for a concert system. These describe the core capabilities. And then we have the non-functional requirements, which define the qualities of the system. Think about things like booking tickets should have low latency, or maybe the system must scale to millions of users. These qualities are absolutely critical because they often dictate the fundamental architectural choices you'll make later on.
That's such a vital distinction, isn't it? So many engineers, especially early on, they jump straight to the functional side, what button does what.
Mm-hmm.
But the non-functional requirements, those behind-the-scenes qualities, they truly differentiate a good system from a great one. They force you to think about resilience, performance, maintainability right from the get-go. In my experience, the real aha moment isn't just knowing these trade-offs exist. It's understanding that system design is less about finding the right answer and more about, mastering the art of intentional compromise based on what the business actually needs.
Precisely. Intentional compromise. I like that. Okay, so once those requirements are clear, you start defining your core entities. What data does the system need to persist?
The nouns of your system.
Yeah, exactly. For our concert system example, that might be users, events, tickets. These often map pretty directly to tables in a database or the objects your API will exchange. From there, you outline the basic APIs. How will clients actually interact with your system? Most often, you're looking at REST endpoints, right?
Yeah.
Representational state transfer.
The default, usually.
But we'll see, there are specific scenarios where maybe GraphQL, that powerful query language, or even RPC, remote procedure call, might make more sense.
Definitely specific use cases for those.
With those basics in place, you move to a high-level design. This is where you sketch out the main components, your initial boxes and arrows on a whiteboard, basically, to meet those functional requirements. It's about getting a simple working blueprint first, but that's just the beginning, isn't it?
Oh, yeah. That's where the real fun starts.
The real depth and the truly fascinating part comes in what we call the deep dives within the design process. This is where you enhance that initial high-level blueprint to meet all those critical non-functional requirements. How do you ensure low latency for ticket booking? How do you guarantee strong consistency to prevent double bookings? How do you make it scale to handle a massive surge of users?
Right, the hard problems.
This is where you bring in specific technologies and design patterns, which is exactly what we'll be exploring today. And finally, when you're evaluating a system design, it's about more than just getting to a right answer. It's about your problem-solving skills, like can you recognize and prioritize the core challenges? It's about your solution design. Did you weigh trade-offs and arrive at something that truly works for the given constraints? And critically, it's about your technical excellence.
Ah, yes, technical excellence. That's key.
Can you go deep into specific technologies, understand their nuances, and anticipate where things might break? Plus, of course, clear communication is key to explaining complex concepts.
Absolutely. Your technical excellence, for instance, it isn't just about reciting definitions. It's about demonstrating How your chosen technologies and patterns directly address those crucial non-functional requirements you identified,
Right.
and how they perform under stress. It's about reasoning through potential failure modes, trade-offs.
Yeah.
This systematic approach is what truly distinguishes a robust system design. It's moving beyond just knowing the facts to applying them strategically.
Okay. Building on that framework, especially when we talk about those vital non-functional requirements for distributed systems, there's one fundamental starting point that dictates so many downstream decisions, the CAP theorem.
The cornerstone, really.
If you walk into any system design discussion, whether it's an interview or a real-world architectural meeting, this is often the first question you need to ask yourself. Does the system need to prioritize consistency or availability?
That choice drives everything.
So what exactly is the CAP theorem? It states that in a distributed system, you can only pick 2 out of 3 core properties: consistency, availability, and partition tolerance. Let's quickly define these. Consistency means that all users see the same, most up-to-date data at the same time, regardless of which server they connect to. It's about data being uniform across your entire system.
Everyone sees the same truth.
Availability means that every request gets a response, whether it's successful or an error. The system always responds, even if the data might be temporarily stale.
It always picks up the phone, basically.
And partition tolerance means the system continues to operate despite network failures between nodes. Think of network partitions as a complete loss of communication between parts of your distributed system nodes simply cannot exchange messages.
And this happens all the time.
Right. In today's world, where systems are inherently distributed across data centers, continents even, network failures are a given. They are unavoidable. So in almost every distributed system you'll ever design, partition tolerance is effectively a must-have.
This point about partition tolerance being a given is crucial. It's not really an option you choose to have. It's a reality of distributed computing. Networks will fail. Segments of your system will lose communication.
Yeah.
So the real decision isn't whether to have partition tolerance, but what you prioritize when it inevitably happens.
Exactly. And that leaves us with the core trade-off. In a distributed system with partition tolerance guaranteed, you must choose between consistency and availability. You simply can't have both strong consistency and high availability simultaneously during a network partition.
Can't have your cake and eat it too, network-wise.
Pretty much. Let's illustrate this with a classic example. Imagine you host a website with 2 servers, one in the USA, one in Europe.
Check it.
A user in the USA writes some data, say updating their public profile. This data is supposed to be replicated to the European server. Now, what happens if the network connection between these 2 servers gets severed before that data has a chance to replicate?
The dreaded network partition.
Right. When a user in Europe tries to read that same profile data, what should the system do? Well, if you choose to prioritize consistency, you're building what's often called a CP system. In our example, the European server would stop serving data for that profile to prevent showing stale information. It would likely return an error.
So it sacrifices availability to ensure correctness.
Exactly. This guarantees that all users, no matter where they are, see the exact same most recent data, even if it means temporary unavailability for some requests. This is absolutely essential for scenarios where data accuracy is paramount, like ticket booking systems. You absolutely cannot allow double bookings for the same seat.
Or banking applications. Incorrect balances are a disaster.
Right, you'd rather have an error than an incorrect balance. On the other hand, if you choose to prioritize availability, you're building an AP system. In this scenario, the European server would continue serving data, even if it knows that data might be stale because of the network partition.
So it prioritizes responding even if the data isn't perfectly fresh.
Yeah. Users might temporarily see an older version of the profile, but they will always get a response. This is perfectly acceptable for systems like, say, social media feeds or news websites.
We're seeing an older post for a moment isn't the end of the world.
Exactly. Having the service always respond is more important than immediate global consistency in those cases. Now, it's important to understand that consistency isn't just one thing, right? While we often talk about strong consistency in the context of C-key theorem, meaning all reads reflect the most recent write, there's actually a spectrum of consistency models.
The nuances. Good point.
Strong consistency is what we just discussed, crucial for things like bank balances, most expensive performance-wise. Then there's causal consistency, which ensures that related events appear in the same order, like a comment must always appear after the post it's commenting on.
Makes sense. preserves the cause and effect relationship.
Read your own rights. Consistency guarantees that you will always see your own updates immediately, even if others might see an older version for a bit. Common in social media profile updates.
So you don't get confused thinking your update didn't save.
Right. And finally, eventual consistency is the most relaxed form. The system will become consistent over time, but temporary inconsistencies are allowed. This is the default for many distributed databases prioritizing availability. Think DNS updates propagating.
Okay, so AP systems often default to eventual consistency.
Pretty much. And this choice, CP versus AP, also directly influences your database choices. For systems prioritizing consistency, you'd typically lean towards relational databases like PostgreSQL or SQL Server.
The traditional choices for strong guarantees.
Though it's worth noting some NoSQL DBs, like DynamoDB, can offer strong consistency modes for specific operations. It's not usually their default, though.
Right, you have to opt in, usually with performance trade-offs.
If you prioritize availability, you'll design systems with multiple replicas, scale-out architectures, technologies like DynamoDB, especially configured across multiple availability zones, or Canandra, which is optimized for high availability, become prime candidates.
Build for scale and resilience.
Even changed data capture, or CDC, which pushes updates between databases, is often eventually consistent and fits well into this AP model.
That decision consistency or availability really does ripple through every subsequent design choice you make. Your database, replication, how you handle client requests during failures. It all stems from that initial trade-off.
Which naturally leads us to, how do those clients actually talk to our systems when the network is, well, fundamentally unreliable?
Exactly. It's the plumbing, right?
Right.
Often invisible until it breaks.
Precisely. We talk about databases and APIs, but at the heart of any distributed system is something often taken for granted, something that feels under the hood but is absolutely critical: network communication.
Can't distribute without the network.
Your services don't live in a vacuum. They need to talk to each other and to the outside world. Understanding the basics of how networks operate, even at a high level, is paramount for making informed design decisions and, frankly, for debugging when things inevitably go wrong.
Oh, absolutely. Debugging network issues can be brutal if you don't grasp the fundamentals.
We often simplify the complex OSI model for system design, focusing on the layers most relevant to developers. Let's start with layer 3, the network layer. This is where IP addresses live.
The street addresses of the internet.
Basically, yeah. IP addresses are how data packets are routed across networks, telling a packet where to go. You have public IP addresses, which are internet-facing, letting outside clients reach your services, and private IP addresses used for internal communication between your microservices or other internal hosts.
So, public for the front door, private for inside the house.
Good analogy. When you set up a load balancer or manage internal service communication, you're constantly dealing with these IP addresses. Moving up, we have layer 4, the transport layer. This is where protocols like TCP, Transmission Control Protocol, and UDP, User Datagram Protocol, reside. These build on top of IP. TCP is typically your default choice for most applications. Why? Because it provides crucial guarantees: guaranteed delivery and guaranteed ordering of packets.
The reliable postal service. It gets there, in the right order.
Exactly. When you establish a TCP connection, there's a bit of a back and forth, three-way handshake that sets it up. This adds a tiny bit of overhead and means both client and server have to maintain state about the connection.
There's a cost to that reliability.
There is. But that cost is often worth it because TCP handles retransmissions if packets are lost and ensures data arrives in the correct sequence. Its reliability is its strength, but it can impact throughput and add latency, especially over dodgy or long-distance networks.
Right. All that checking and resending takes time.
Then there's UDP. You can think of UDP as a spray and pray approach.
Or like a machine gun just firing packets out.
Yeah. It sends data without any guarantees of delivery or ordering. If a packet gets lost, UDP doesn't care. It just keeps sending the next one. This might sound terrible, but it's incredibly useful for real-time, loss-tolerant applications, like video conferencing. If you drop a frame, it's better to just skip it and keep the stream going than to wait for retransmission, which would introduce noticeable lag.
Or online games. Same principle. Dropping a position update is better than freezing the game.
Exactly. The trade-off is higher performance and lower latency, but you, the application developer, have to handle any missing data or out-of-order packets if it matters.
More work for the app, less work for the network layer.
And it's worth noting, browsers don't natively support UDP, so for web apps, you're generally sticking with TCP-based stuff. Though QUIC is emerging as a modern alternative built on UDP, aiming for TCP's reliability with UDP's speed.
QUIC is interesting, trying to get the best of both worlds.
Finally, at the very top is Layer 7, the application layer. This is where developers typically operate. Protocols like HTTP, WebSockets, DNS live here, built on top of TCP or UDP.
Our usual playground.
A key distinction here is that this layer is processed in user space, meaning it's highly flexible, easily modifiable by us developers. Lower layers like TCP and IP operate in kernel space, which makes them incredibly efficient, but also much harder to change.
Right, closer to the metal, harder to tweak.
Understanding this helps you appreciate why certain optimizations happen at different layers of the stack.
And to zoom out for a moment, understanding these layers helps you reason about performance bottlenecks. Is the lag in the TCP handshake across the Atlantic? Or is it my application code taking ages to process the HTTP request?
Good point. Knowing where to look is half the battle.
Absolutely. The higher you go in the stack, the more abstraction, but often more latency and overhead too. It's all trade-offs, as usual.
Okay, so we've thought about the foundation's Kappu theorem, networking. Now, the next critical step. How do clients actually interact with our system? This brings us right into API design.
Crafting the contract.
It's essentially the contract between your system and the outside world. When you're discussing API design, say in an interview, you'll typically choose from three main protocols. Your default choice, often the simplest and most straightforward, is REST, Representational State Transfer. REST uses standard HTTP methods, get, post, put, delete, to manipulate resources identified by URLs.
Maps really well the CR operations. Create, read, update, delete.
Exactly, and it leverages the existing semantics of HTTP. So to retrieve a user, you'd use get users to update them, put users with the new data. To create a new user, post users. The key here is thinking in terms of resources, like nouns and operations on them, rather than procedural methods like verbs.
Right. PuT users, not update user.
Precisely. REST is the go-to for most web and mobile apps because it's simple, stateless, easy to scale horizontally behind a load balancer.
It's well understood, widely adopted.
But REST's fixed endpoints can sometimes present challenges, right? And that's where GraphQL emerged, famously from Facebook back in 2012.
Solving the overfetching, underfetching problem.
Exactly. Their mobile app needed different data than their web app, but REST endpoints returned fixed structures. This often led to either tons of specific endpoints or, more commonly, overfetching clients downloading way more data than they needed.
Wasting bandwidth, especially on mobile.
Or underfetching, where clients had to make multiple separate API calls just to get all the necessary data for one screen.
Which adds latency.
GraphQL solves this using a single endpoint with a powerful query language. Clients specify exactly what data they need, down to the field level, and the server returns that data in the exact requested format. Imagine our Ticketmaster example. Instead of separate REST calls for event details, venue info, tickets, you could have one GraphQL query asking for just the event name, date, venue address, and ticket prices for available sections.
Super efficient for the client.
Makes it ideal when you have diverse clients with varied data needs, or when front-end teams need to iterate quickly on UI changes without constantly bugging the back-end team for API modifications.
Empowers the front end.
The trade-off, however, is added complexity on the back end. You need query parsing, schema validation, and often pretty sophisticated caching strategies.
It definitely shifts the complexity burden, doesn't it? REST puts it on the client to orchestrate calls. GraphQL puts more on the back end to handle complex queries efficiently.
That's a great way to put it. Beyond diverse clients, I think the tipping point for GraphQL often comes when that front-end iteration speed is absolutely paramount and maybe the back-end team is a bottleneck. GraphQL lets the front end evolve without waiting for API changes.
Makes sense, when front-end agility is the driving force.
The third option is RPC, Remote Procedure Call. Protocols like gRPC, Google's version, use binary serialization, often with protobufs, protocol buffers, and leverage HTTP2 for extremely efficient communication, especially between internal services.
Performance is the key driver here.
Right. Unlike REST's resource focus, RPC lets you think in terms of actions or procedures. If your user service needs to quickly validate permissions with an auth service, an RPC call like check permission user resource feels more natural than modeling it as a REST resource.
Yeah, it's more verb-oriented.
gRPC offers significant performance benefits. Think binary serialization versus JSON over HTTP. It can be much faster. Plus, strong typing catches errors at compile time.
Good for internal service-to-service chatter where performance is king.
Our general recommendation is usually REST for public-facing APIs, especially for clients you don't control. Reserve gRPC for internal service-to-service communication where performance is critical. But importantly, don't prematurely optimize with RPC before you've tackled other, bigger bottlenecks.
Yeah, don't reach for gRPC just because it sounds cool if a simple REST call is
Well,
fine.
exactly. Now, regardless of the protocol, one pattern you will hit with large data sets is pagination. You just can't return millions of records in one go.
Nope. Network timeouts, memory issues, disaster.
Pagination breaks large results into manageable chunks. Two main approaches: offset-based pagination. Simplest. You specify an offset, skip n records, and a limit, return m records. Like events.offset20 and limit 10 gets records 2130.
Intuitive, like flipping pages in a book.
But it has a big drawback with dynamic data. If items are added or deleted while someone's paging, the offset shifts. You can miss records or see duplicates.
The classic pagination bug.
And it gets inefficient for deep pages as the database still has to scan through all the skipped records.
Right. Offset 1 million limit to 10 can still be slow.
Cursor-based pagination solves the stability issue. Instead of an offset, it uses a pointer, a cursor, to a specific record. Your first request might be events.limit10. The response includes the events plus a next cursor value, maybe an encoded ID or timestamp of the last item.
An opaque token, usually.
Right. The next request is events.cursor's semi-opaque value in limit 10. This is stable because it's not affected by data shifts.
Well,
but
it'll jump to page 50 really hard.
Exactly. For interviews, offset-based is often okay to start with, but the key is to remember to include pagination in your API design for any list data. Don't forget it.
This really hammers home that your API is the language your system speaks. Choosing the right dialect, REST, GraphQL, RPC dictates so much. Client interaction, flexibility, performance, back-end complexity. It's a critical decision. As you said with pagination, you got to anticipate scale and design for it from the start.
So, okay, you've designed this great API. How do clients actually connect to your services, especially if you've got a bunch of microservices running around? That's where the API gateway comes in.
The front door.
Yeah, think of it like the really efficient front desk at a fancy hotel. Guests don't need to know where housekeeping is or the maintenance room.
They just talk to the front desk.
Exactly.
Yeah.
Clients of your system shouldn't need to know about all the internal microservices doing the work. The API gateway is that single, unified entry point for all client requests. It manages and routes them to the right backend service.
Decouples the client from the internal messiness.
Precisely. And its evolution really parallels the rise of microservices. Back in the 2000s, mostly monoliths, right? Client hits one URL, one big server, does everything. Simple.
Easy days, relatively speaking.
Then around 2010, 2012, microservices start taking off. Suddenly, clients either needed to know the URL of every microservice,
Which is messy client-side code.
or they'd route everything to one microservice, which then acted as an internal router. But changing that routing logic meant redeploying a whole service. Not ideal.
Yeah, tight coupling again.
So around 2013, 2014, the first API gateways popped up. Just a thin layer, mainly for routing. Clients hit one endpoint, the gateway figures out where to send the request. Solve the routing mess.
Okay, progress.
But then came the realization, all these microservices were repeating tons of boilerplate code. Authentication, rate limiting, logging, SSL termination.
All that cross-cutting stuff.
Right. So from the mid-2010s till now, API gateways evolved to handle that shared middleware too. Now the gateway does routing and these centralized chores. It verifies tokens, throttles abusers, handles cores, compresses responses.
Letting the microservices focus purely on business logic.
Exactly. Client talks to one URL, gateway's the shared guardrail, microservice teams focus on their specific job. If we zoom in on what's happening inside that gateway, first, validating the request. Is it formatted right? Header's okay. Body valid. Reject immediately if not.
Fail fast.
Second, running middleware. This often means super fast calls to external things like Redis for rate limiting or an O service for auth checks. These have to be blazing fast because they run on every request.
Bottleneck potential right there.
Third, routing to the correct services. Using a routing map like Messages goes to the messaging service URL. Simple configuration.
The core routing function.
And finally, it can transform the response. Maybe internal services use gRPC, but the client wants JSON. The gateway handles that translation.
Protocol mediation. Handy.
So when do you propose an API gateway in an interview? Short answer. Almost always when you have a microservices architecture, it's pretty essential for decoupling clients from internal complexity.
Provides that clean separation.
But crucial point, recognize when it's overkill. Simple monolith. Single client system. probably adds unnecessary complexity.
Right, tool for the job. Don't add layers just because.
In an interview, it's usually okay to just mention it, say it handles routing and basic middleware, and then move on to the deeper stuff unless probed. You can mention AWS API Gateway, Azure API Management, open source like Kong.
Yeah, acknowledge it, show you know its role, then focus on the core system logic. Connecting it back, the API Gateway is your control plane for external traffic. It gives you that crucial abstraction, lets internal services evolve independently, but you always have to weigh its benefits against the added complexity. Be deliberate.
Okay, data, the absolute lifeblood of any system, right? We've talked about exposing it via APIs, but a huge challenge is storing it and, just as importantly, getting it back out quickly.
Retrieval speed is often make or break for user experience.
Totally. This brings us to database indexing. It's a fundamental technique for speeding up data queries, especially when slow reads are just, well, intolerable.
Can't have users waiting seconds for basic info.
Let's start with the problem. Without indexing, how do databases store data? Usually on pages, right? Like 8 kilobytes each.
Yeah, chunks of data on disk.
So if you want to find one specific item without an index, the database has to do a sequential scan. It pulls a page into RAM, scans all the rows on that page. Not there. Put it back. Pull the next page. Scan again.
Keep going until you find it or run out of pages. Brutal.
Imagine 100 million users in a table. Even with optimizations, finding your specific user could take several seconds. Way too long for a web request.
Unacceptable latency.
The solution? Indexes. Indexes are special data structures, also stored on disk that acts like a map, or maybe a books index.
Good analogy. Points you right to the page.
Exactly. Instead of scanning millions of pages, the index tells the database exactly which page your item lives on. So a query comes in, the DB pulls a tiny part of the index into memory, quickly finds the pointer to the right data page, and then pulls only that single page into memory.
Drastically reduces the amount of data read from disk.
Huge difference. Read time drops from seconds to milliseconds. Common ways to build these indexes. You could use a simple hash map, which gives you basically constant time lookup, O1, super fast for specific key lookups.
Perfect for exact matches.
Or a sorted list, which allows efficient logarithmic time lookups, O log n, using binary search. Good for range queries, too. In practice, most databases use more sophisticated versions. B-trees are super common in relational DBs like Postgres, and they also underpin things like DynamoDB's sort keys. You also see hash tables and specialized indexes for geospatial data or full-text search.
Lots of different index types for different query patterns.
But the core idea is the same. Do a little bit of upfront work building and maintaining the index.
Which costs something on writes and takes up storage.
Right. There's a trade-off
Yep.
so that your reads can be extra fast.
Yeah. For system design interviews, the general advice is, if your main database offers indexing, use its built-in capabilities.
Absolutely. They've been optimizing these things for decades. Battle-honed, as you said.
Don't reinvent the wheel unless you absolutely have to. Maybe with something like Redis, where you might design your own strategy, but usually use the DB's features. Yeah, this really forces you to balance that cost of indexing the write overhead, the storage, against the read speed gain. It's a classic trade-off. You don't index everything, just what you need to query efficiently. And you have to understand how those indexes impact your writes.
Okay, so when we talk about data storage, the first type of database that usually comes to mind, and often the default choice for transactional data in product design interviews, is the Relational Database Management System, RDBMS. Think PostgreSQL, MySQL, SQL Server.
The workhorses,
Yeah.
been around forever, super robust.
Exactly. At their core, they store data in tables, which are collections of related data. Tables are made of rows, individual records like one user, and columns, the data fields for each record like name, email.
Structured, predictable.
And you interact with them using SQL, that powerful declarative language for querying. Beyond just storing data, RDBMS offer key features super relevant for system design. First, SQL joins let you combine data from multiple tables based on relationships.
Like getting all posts for a specific user from the users and posts tables.
Right. Incredibly flexible. But, warning, arbitrary joins, especially across huge tables, can become major performance bottlenecks. You want to minimize them if possible.
Yeah, joins can kill performance if not done carefully. often requires denormalization later.
Second, indexes. We just talked about indexing generally, but relational databases really excel here. You can create tons of indexes on single columns, groups of columns.
Optimizing for all sorts of different queries.
They support multi-column indexes, specialized indexes like geospatial or full text, often implemented with super optimized B-trees or hash tables.
Very flexible indexing capabilities.
And perhaps most importantly for critical business logic, ACID transactions. ACID stands for atomicity, consistency, isolation, durability.
The gold standard for data integrity.
It means you can group multiple database operations into a single, indivisible unit. Either all operations in the transaction succeed or all of them fail and roll back.
All or nothing.
Crucial for maintaining data integrity. Think bank transfers. Debit one account and credit another. A transaction ensures if the credit fails, the debit is also rolled back. No money vanishing.
Prevents those horrible inconsistent states.
Or creating a user in their first post together. A transaction ensures you don't get a post from a user who doesn't exist. These strong guarantees are essential for anything needing absolute accuracy.
It's fascinating, isn't it? While NoSQL often gets the hype for scale in distributed systems, the robust transactional guarantees and flexible querying of relational databases make them incredibly powerful for that core business logic where strong consistency is non-negotiable. They're often the right choice until you genuinely hit a scale bottleneck that forces you towards more distributed options.
Right. It's not about better, it's about the right tool for the specific job and constraints. Speaking of scaling beyond relational, let's dive into the world of NoSQL. These databases often came about precisely because traditional relational databases struggled with, well, massive volumes of data or extreme traffic levels. One of the big players in the NoSQL space, especially in the cloud, is DynamoDB, Amazon's fully managed NoSQL service. It's really optimized for high performance and immense scalability. You see it a lot in system designs.
Yeah, very popular choice for AWS users needing scale.
Let's break down its data model. Like SQL, data is in tables. Inside tables, you have items, like rows, each with a unique primary key. And items have attributes, like columns. The big difference here is its schemaless or flexible schema. Items in the same table can have different attributes. Some users might have an employer attribute, others don't.
Which is great for agility. No migrations needed if you add a field to some items.
Exactly. Pros, fast, flexible, pay only for what you store. Cons, your application has to handle potentially missing attributes. Data analysis can be trickier.
Right, the database doesn't enforce a rigid structure. That's on your application code.
The most crucial concept in DynamoDB for organizing and retrieving data is the primary key. It's a combination of a partition key and an optional sort key.
This is fundamental to understanding DynamoDB performance.
The partition key is the main identifier. DynamoDB uses consistent hashing on this key to figure out the physical storage location which partition or node the item lives on. The sort key, if you use one, is a secondary attribute that allows ordering and range queries within a specific partition.
Super useful, like timestamp for sorting items within a partition.
Yeah. Example, a chat app. Chatted is your partition key. Message ID, maybe a timestamp-based UUID, is your sort key. This lets you efficiently grab all messages for one chat, sorted by time, all from a single partition. Very fast.
Designing around that partition key is everything.
DynamoDB also offers secondary indexes for querying on attributes not in your primary key or for different sort orders. Two types. Global Secondary Index, GSI, has a different partition key than the main table. It maintains its own separate partitions and replicas. Huge query flexibility.
But it eventually consistent only, that's the catch.
Right. Updates to the main table might take a short while to show up in the GSI. Great for global search, though, like finding messages by user ID across all chats. Local Secondary Index, LSI, uses the same partition key as the main table, but a different sort key, stored locally with the base table items.
So queries are scoped within that main partition.
Exactly. Supports both eventual and strong consistency reads. Useful for querying within a partition on a different attribute, like messages in a specific chat by new attachments.
Fewer LSIs allowed per table than GSIs usually.
Yeah.
And size limits per partition.
Good point. Now, accessing data. Two main ways. Query and scan. Query is efficient. It retrieves items based on the primary key or secondary index keys. This is what you want to use.
Targeted retrieval.
Scan, on the other hand, reads every single item in a table or index. Highly inefficient for large tables. Avoid it in production if you possibly can.
Can burn through your provision capacity very quickly and be slow.
And a critical point. DynamoDB reads the entire item by default. If you have huge items, consider normalizing maybe store large text blobs in a separate table linked by ID to avoid costly overfetching.
Good tip. Don't pull back massive items if you only need a few fields.
DynamoDB also supports transactions now for atomic operations across multiple items or tables. Similar idea to ACID. Under the hood, consistent hashing on partition keys distributes data. Asynchronous replication provides fault tolerance writes go to a leader, then replicate to followers in different availability zones.
Standard distributed system patterns for scale and availability.
So, when to use DynamoDB in an interview? Excellent for highly scalable, low latency, key value lookups, high volume reads writes where you have clear access patterns defined by your partition and sort keys.
If you know exactly how you'll query the data, it's often a great fit.
But avoid it for complex ad hoc queries, multi-table joins, or if you need strong consistency everywhere and can't tolerate eventual consistency nuances.
DynamoDB really forces that query-driven design mindset we talked about. You build your data model around how you'll access it. It's a shift from relational thinking, but unlocks massive scale.
Okay, let's move to another major NoSQL player, Cassandra. It's a distributed database, often picked when the priority is availability and extremely high write throughput, designed to be always on, basically.
Yeah, known for its resilience and write performance. Popularized by Facebook originally.
Let's look at its data model. Top level is a key space, like a database in SQL land. Holds tables and configuration like replication strategy. Inside a key space, you have tables. Tables contain rows. Each row is unique by its primary key and holds columns. Now, Cassandra is a wide column database. This means columns can vary per row in the same table. Schema flexibility again.
Like DynamoDB's flexible attributes.
And every column has a timestamp. Write conflicts between replicas resolved using last write wins.
Which prioritizes availability, but means you might lose an update if clocks are skewed or writes arrive out of order. Eventual consistency implications.
You can think of Cassandra data like big JSON objects. Supports diverse types. Like DynamoDB, the primary key is critical. It's made of one or more partition keys and 0 or more clustering keys.
Same core concept. Partition key determines the node partition. Clustering key determines the order within that partition.
Exactly. An example primary key might be evented section seeded. Here, evented sectioned is the composite partition key. Seeded is the clustering key.
Understanding how to choose these keys is paramount for performance.
Cassandra's big strength, especially for writes, comes from its storage model. It uses a log-structured merge tree, LSM tree index.
Unlike B trees used in many other databases.
Right. Cassandra fundamentally favors write speed. Every create, update, delete is just a new entry appended to a log. Super fast writes because it's just appending.
Append only. Makes writes sequential, very disk-friendly.
The state of a row is determined by the sequence of these updates. Deletes are special tombstone markers. Reads have to potentially merge data from multiple places. Memory, different disk files, which is why reads can sometimes be slower than writes.
The trade-off for that amazing write throughput.
Data modeling in Cassandra is absolutely query-driven design. You must design your schema around how your application will query the data.
You can't just design tables and then figure out queries later, like in SQL. You start with the queries.
It involves thinking hard about the partition key, potential partition size, you don't want partitions getting too huge, the clustering key for sorting, and often data denormalization.
Denormalization is key in Cassandra. You often duplicate data into multiple tables, each optimized for a specific query pattern.
Let's take a real example. Discord messages. High volume. Users mostly query recent messages.
Classic Cassandra use case.
Initially, they used channelid as the partition key. All messages for a channel on one node. Good for reads. But busy channels meant huge, ever-growing partitions, performance killer over time.
The unbounded partition problem.
Their solution? Add a bucket based on time, like 10-day chunks, to the partition key. So the key became channelid, bucket. This caps partition size. New data goes into new time buckets. Recent messages are still efficiently queryable.
Smart. They managed partition size while keeping recent data reads fast. Query-driven thinking.
So when to use Cassandra? When you prioritize availability over strict consistency, need high scalability, need high write throughput, thanks LSM tree, want flexible schemas, and have clear, defined access patterns.
If those conditions fit, it's a beast.
But not for strict consistency needs, not good for complex ad hoc queries, JOINs, or heavy aggregations.
Again, connecting it back, Cassandra shows that designing around how you query rather than a rigid relational model unlocks immense scale, especially for write-heavy systems. It forces deep thinking about data distribution and access patterns right up front.
Okay, databases are great for structured data, metadata. But what about massive unstructured files? Images, videos, big documents.
Yeah, the stuff databases tend to choke on, blobs, binary large objects.
Exactly. Storing large blobs directly in a traditional database, usually a bad idea. Performance tanks, replication gets slow and expensive, backups become enormous and slow to restore.
Increases memory pressure, replication lag, just painful.
Databases just aren't built for it. The solution: specialized object storage or blob storage services. Think Amazon S3, Google Cloud Storage, GCS, Azure Blob Storage.
Purpose-built for this exact problem.
Under the hood, simplistically, they store your files on cheap storage nodes, disks spread across data centers. A separate metadata service tracks where each file lives.
So metadata lookup first, then direct access to the storage node.
Right. Key characteristics making them ideal. Durability. Insanely durable. S3 talks about 11 nines of durability, achieved through massive replication, erasure coding across servers, racks, data centers.
Your data is almost certainly safer there than anywhere else.
Scalability. For interviews, assume they're infinitely scalable. Unlimited storage, unlimited requests. Scalability is basically handled for you.
Takes a huge operational burden off your shoulders.
Cost. Way, way cheaper than storing blobs in a database. Orders of magnitude difference often.
Storage cost is much lower.
Security. Built-in encryption, at rest, in transit, robust access control, common use cases. Storing photos, videos, YouTube, Instagram, user uploads, Dropbox, static web assets, CSS, JS, images often fronted by CDNs, log files, ML training data.
Anything big and unstructured, basically.
A crucial pattern to remember: store metadata in your DB, store the blobs in object storage.
Yes. This comes up all the time.
For a social media post with an image, store post ID, creator, text in Postgres or DynamoDB. Store the large image file itself in S3. The database record just holds a URL or link to the S3 object.
Fast queries on metadata, cheap scalable storage for the big file, best of both worlds.
Another powerful feature: direct upload download with pre-signed URLs. Instead of the client uploading to your server, then your server uploading to S3.
Which doubles bandwidth and loads your servers.
Right. Your server asks S3 for a temporary, permissioned, pre-signed URL. The client uses that URL to download directly from S3, bypassing your server entirely.
Much more efficient, saves server resources and bandwidth costs.
Finally, for really huge files, gigabytes, terabytes, chunking, or multi-part upload, HTTP has size limits. So you break the huge file into smaller chunks, like 5 MB, upload these chunks potentially in parallel. S3 or GCS Azure stitches them back together.
Also allows resuming failed uploads. You only re-upload the failed chunks.
Exactly.
What's fascinating here is just recognizing the fundamental difference between structured metadata and large binary data. It's a hallmark of effective system design. Don't force your database into a job it's bad at. Use the specialized tool object storage for the specialized job. Separation of concerns wins again.
Okay, so as systems grow, we need to distribute data across more servers. Add more database nodes, cache nodes. But how do you do that efficiently? Especially when adding or removing servers, doing it naively can cause chaos.
Well, yeah, the redistribution problem can bring systems to their knees.
This is where consistent hashing comes in. It's a really foundational algorithm for distributed systems that solves this problem elegantly. Let's first see the problem with the simple approach: modulo hashing. Say you distribute event data across databases using database hash evented percent number of databases.
Simple hash, then modulo the number of servers. Seems straightforward.
Works fine if you have, say, 3 databases. Event ID hashes modulo 3 tells you database 0, 1, or 2. But what happens when you need to add a 4th database? You change the formula to hash evented 4.
Uh-oh. The result of the modulo changes for almost everything.
Exactly. An event that was on database 1, hash per 3, forces 1, might now need to move to database 0, hash per 4 equals 0. Almost all your data gets reassigned. This triggers massive, unnecessary data shuffling across all instances.
Huge load spikes, slow responses, potential downtime. Disaster.
Same thing happens if you remove a database. Simple modulo hashing just doesn't scale gracefully. Enter consistent hashing. The clever idea is to arrange both data keys and servers on a conceptual circle, a hash ring. Imagine points from 0 to, say, 100.
Okay, circular space.
You place your servers, database 1, 2, 3, at points on this ring. To figure out where an event goes, you hash its ID to get a point on the ring. Then you walk clockwise from that point until you find the first server. That event belongs to that server.
So data is assigned to the next server clockwise on the ring.
Right. Now, the magic happens when you add or remove a node. add a new database 5 at position 90. It only needs to take data from its immediate clockwise neighbor, say database 1 at position 0. Specifically, it takes the data hashed between its counterclockwise neighbor, say database 3 at 75, and itself at 90. Data from 7590 that was on database 1 now moves to database 5.
Crucially, data belonging to database 2 and database 3 is completely unaffected.
Exactly. Only a small localized portion of the data needs to be moved. Minimal redistribution. Same principle when a node is removed, it dramatically reduces the chaos.
Much more stable during scaling events.
However, a simple ring can still lead to uneven load, maybe servers cluster, or one server gets unlucky and owns a huge arc of the ring, or a server fails and its neighbor gets double the load.
Hotspots or unbalanced load after failure.
Yeah. The solution: virtual nodes, VNs. Instead of mapping one point on the ring to a physical server, you map multiple points, VNs, to each physical server.
So each physical server pretends to be multiple smaller servers scattered around the ring.
Right. This spreads the load much more evenly. If one physical server fails, its VNode's load gets distributed across many other physical servers, not just one neighbor. More powerful servers can own more VNs.
Smoothed out the distribution and failure impact. Standard practice now.
When does this come up in interviews? Well, many systems we've discussed, DynamoDB, Cassandra, Redis clusters, CDNs, use consistent hashing or variations under the hood. You often just need to mention it.
Sure, you know how they handle sharding internally.
But it becomes crucial if you're in an infrastructure-focused interview and asked to design a distributed system from scratch, like a distributed database, cache, or a message broker. Then you need to explain how you'd use consistent hashing.
What's fascinating is how this simple geometric idea, arranging things in a circle, solves such a massive scaling problem. It fundamentally changes how distributed systems manage data placement and rebalancing. It's really elegant algorithmic thinking.
Okay, moving on. When you're building large-scale distributed systems, especially dealing with streams of events or needing asynchronous processing, you often need a really robust, reliable messaging system. Enter Kafka.
The big name in distributed streaming platforms, message queue stream processor, does a lot.
Let's use a motivating example. Imagine a website showing real-time World Cup stats. Every goal, foul, substitution is an event. Initially, one server produces events onto a queue, another consumes them to update the site.
Simple queue setup.
Problem 1. World Cup expands, 1,000 games simultaneously. Single queue server melts. If you just randomly split events across multiple queues, chaos. Goals before matches start.
Order matters a lot.
Solution: distribute events based on game ID. All events for Game 1 go to Q1, Game 2 to Q2, etc. Ensures order per game. This introduces Kafka's core idea, user-specified distribution strategy, via a partitioning key.
You control how related messages are grouped.
Problem 2. Even with distributed queues, the single consumer is overwhelmed. Add more consumers. Now the same goal gets processed twice. Duplicates.
Need coordination between consumers.
Solution: consumer groups. Within a group, each event, or partition really, is processed by only one consumer. Prevents duplicates, allows horizontal scaling of processing.
Key concept for parallel, non-duplicated processing.
Problem 3. Expand to basketball. Don't want soccer consumers getting basketball events.
Needs logical separation.
Solution: topics. Events associated with topics. Soccer events, basketball events. Consumers subscribe only to topics they care about.
Filtering at the topic level.
Okay, Kafka terminology. A broker is a server in the Kafka cluster, holds partitions. A partition is the physical storage unit, an ordered, immutable, append-only log file on disk. Think of it like one segment of a distributed queue. A topic is a logical grouping of one or more partitions. Producers write to topics, consumers read from topics. A producer writes messages, a consumer reads messages. A message, or record, has a required value and optional key, timestamp, headers. That key is critical for partition selection. If provided, Kafka hashes the key, hashkey %num partitions, to deterministically assign the message to a specific partition. No key, random assignment, round robin usually.
So choosing a good key is vital for ordering and even load distribution.
The append-only log design of partitions is central. Benefits: immutability, simplifies replication, recovery. Efficiency, minimizes disk seeks. Scalability, add partitions brokers horizontally. For fault tolerance, Kafka uses replication. Each partition has a leader replica, handles reads writes, on one broker, and follower replicas on other brokers that passively copy data. If a leader fails, an in-sync follower is promoted. A controller node manages all this.
Standard leader-follower replication pattern.
When to use Kafka in an interview. 2 main scenarios. As a message queue. For async processing, like video transcoding store video in S3, put S3 URL in Kafka message. For ensuring order, virtual waiting queue for Ticketmaster. For decoupling producers, consumers, and microservices as a stream. For real-time processing of continuous data feeds.
Log aggregation, real-time analytics, event sourcing.
Right. Now, scalability considerations. Message size. Keep under 1 MB ideally. Don't store blobs in Kafka. Use object storage and put pointers in messages.
Kafka is for metadata and events, not giant files.
Scaling. Add brokers. Increase partitions per topic, but watch out for hot partitions. If one key gets way more traffic, like a super popular ad ID, that partition becomes a bottleneck.
Requires careful key design or strategies like repartitioning or maybe using more granular keys.
Managed Kafka services, Confluent Cloud, AWS, MSK, help, but understanding concepts is key. Performance optimization. Good partition key is paramount. Compression helps throughput. Retention policies are configurable per topic.
How long do you keep the data in the log? Days, weeks, forever? Trade-offs?
Finally, reliability. Handling retracers. Producers have automatic retries. Enabling idempotent delivery prevents duplicates on retry. Consumers. Kafka doesn't have built-in retries like SQS. You need custom logic.
Right. Often involves moving failed messages to a retry topic, then eventually a dead letter queue, DLQ for investigation.
And crucial, offset committing. Commit the offset, marking a message as processed, only after you've successfully persisted the data downstream, even when it will save the crawled HTML to S3. Otherwise, a consumer crash could mean reprocessing messages you already handled.
Exactly. At least once versus exactly once. Processing implications hinge on careful offset management. Kafka provides the backbone, but the art is in the partition strategy, key selection, and robust error handling in your producers and consumers. That's where you ensure order and reliability at scale.
Okay, so sometimes disk-based systems, even fast ones like Kafka or SSD databases, aren't fast enough. When latency is absolutely critical, you need in-memory speed. That's where Redis comes in.
The in-memory data structure store, much more than just a cache.
Totally. At its core, Redis is like a super fast dictionary mapping keys to various data structures. Not just strings, but lists, sets, hashes, sorted sets, streams, geospatial indexes.
A whole toolkit of structures, all held in RAM for speed.
Commands operate directly on these keys, manipulating the specific structures. Understanding its infrastructure configurations is important. Can run as a single node, simplest, but data loss on crash before disk flush. Can run with a high availability, HA replica, master replicates the secondary.
For basic fault tolerance.
Or as a full cluster, multiple nodes. Clients cache a hash slot mapping which key range lives on which node. Clients then try to connect directly to the correct node holding the data.
Minimizes hops, maximizes performance. Redis expects data for one request to be on one node.
Which means how you structure your keys is fundamentally how you scale Redis. You design keys so related data lives on the same node if needed for multi-key operations.
Key design is critical for clustering.
Let's look at its capabilities and common uses. Redis as a cache, most common use case. Keys values map perfectly, distributes easily across a cluster.
Straightforward key value caching.
You almost always use time to live, TTL, on keys for automatic expiration. Manages cache size, prevents stale data, doesn't inherently solve the hot key problem, one key getting hammered on one node. A crude fix. Append a random number to the hotkey to spread load.
Yeah, cache busting with randomness. Effective if messy.
Need to think about eviction policies. LRU, LFU, FIFO, and cache invalidation strategies. How to remove update cache when DB changes. And cache write strategies. Write through, write around, write back. Each has trade-offs for consistency versus performance.
Always be explicit about what you're caching and why.
Redis as a distributed lock. For consistency during updates like Ticketmaster ticket holds, or preventing simultaneous actions, Uber write assignment. Use if your main DB can't provide the necessary lock or consistency guarantee.
Adds complexity? Use judiciously.
Simple lock. Use atomic INCR with a TTL. If it returns 1, you got the lock. If 1, someone else has it, wait, try. DEL the key when done. More complex. Red lock algorithm.
Trade-offs around fairness, timeouts, complexity.
Redis streams for async job queues. Redis streams are like distributed append-only logs, similar to Kafka, but simpler, in-memory focused. Great for ill-synced job queues.
Lightweight alternative to Kafka for some use cases.
Items added to a stream. Consumer groups track progress. Workers query for unallocated items. Only one worker claims an item. Supports fault tolerance via reclaiming items if a worker fails. very fast.
Need to handle Redis failures, though, replicas, clustering.
Redis sorted sets for leaderboard stop in, sorted sets store members with a score ordered by score, super efficient for top N or range queries, logarithmic time for a single key, classic leaderboard implementation. Also powers geospatial indexing, GeoADD with lat-lonid. GeoZirac finds nearby items within a radius, uses GeoHash internally to map coordinates to scores in a sorted set.
Great for find nearby X features, but need to consider sharding for global scale.
Redis PubSub for real-time communication. Servers talking to each other like in chat rooms. Clients subscribe to channels, publishers send messages.
Often the backbone of a WebSocket notification service. Internal services publish to Redis, Edge service subscribes, and pushes to connect to clients.
Exactly. It's incredibly versatile.
What's fascinating is how Redis, fundamentally a simple key-value store, becomes this Swiss Army knife by offering these rich data structures directly in memory. Each structure is optimized for specific access patterns and real-time needs, turning potential bottlenecks into high-performance features.
All right, sometimes simple key-value lookups or basic database queries aren't enough. What if users need to find information within large, maybe unstructured data sets, like searching products on an e-commerce site or articles in a knowledge base?
Yeah, when complex search and relevance are key, that's where Elasticsearch shines.
It's a search-optimized database built for these complex scenarios: full text search, geospatial search, aggregations, relevance ranking. Let's hit the core concepts. Primary data unit. A document, basically a JSON blob. Documents live in an index, which is the collection you want to search. A mapping defines the schema for an index, how fields should be indexed and searched. Like price is a float, description is text for full text, category is keyword for exact matches.
Explicit mapping is important. Avoids guessing, ensures fields are treated correctly for different search types. Text versus keyword is a common distinction.
Elasticsearch has a RESTful API. Put you to create an index, POST to add documents. Search and sorting is where it gets powerful. Basic sorting. Use sort parameter by fields. Price.ascii, it2c, publishdate.des. Simple. Relevance-based sorting. The default. Sorts by score, based on algorithms like TF-IDF, term frequency inverse document frequency.
FIDF, the classic relevance score.
Right. It gives higher scores to terms that appear often in one document, term frequency, but rarely across all documents, inverse document frequency. Makes results more relevant by boosting unique, important terms.
Finds documents that are about the search terms, not just containing them.
How does it work internally? It's built on Lucene, a Java search library. Its core data structure for full text search is the inverted index.
The heart of fast text search.
It maps words, tokens, to the document IDs containing them, like search, doc.c1, doc.c5, doc.10. Searching for fast search. Find docs with fast, find docs with search, combine the lists. This involves tokenization, splitting text, and stemming lemmatization, reducing words to root form running, run.
Handles language variations.
Elasticsearch also uses immutable segments. New documents go into new segments. Existing ones aren't modified. Benefits: better write performance, caching, concurrency, recovery, compression, faster searches.
Immutability simplifies a lot of distributed problems.
It has a smart query planner using statistics to optimize queries. And its cluster architecture typically has ingest nodes, pre-process docs, data nodes, store index, and coordinating nodes, handle client requests, parse queries, merge results.
Standard distributed setup for parallelism and fault tolerance.
For pagination, uses from size, but search after is better for deep pages. Also supports point in time, PIT, search to snapshot the index for consistent pagination during updates.
Solves that annoying page shifts while scrolling problem.
Yeah. When to use Elasticsearch in an interview. Complex search scenarios. Full text, geospatial, vector search. Often paired with a primary database, Postgres, DynamoDB, via change data capture, CDC, to push updates into Elasticsearch.
Meaning Elasticsearch is usually eventually consistent with the source of truth.
Exactly. Now, limitations and lessons. Not a primary database. It's a search engine. Don't rely on it for durable transactional storage.
Use it alongside a proper database.
Performs best on read-heavy workloads. Can struggle with very high write rates. Eventual consistency. Results will be slightly stale. Unsuitable for strong consistency needs. No double bookings.
Critical limitation to understand.
Denormalization is key. Flatten your data for search. Avoid joins, not always needed. For small datasets or simple searches, DB queries might be fine. Elasticsearch clusters are complex to operate.
Don't introduce it unless the complexity is justified by the search requirements.
And synchronization failures via CDC are a common source of bugs.
Keeping it perfectly in sync is hard. Connecting it back. Elasticsearch is a masterclass in building a specialized, performant distributed system using things like immutability and inverted indexes. But it starkly highlights the trade-offs, especially around consistency. It's powerful, but demands careful consideration of where it fits and its limitations.
Okay, we've covered databases giving exact answers, search engines giving powerful, if eventually consistent results. But what about scenarios with truly massive data sets or super high throughput streams where getting an exact answer is just too slow, too costly, or maybe even impossible with reasonable resources?
Yeah, when you hit computational or memory limits for exact calculations.
This is where specialized data structures come in, offering incredibly memory-efficient and fast approximate answers. A quick caveat. For newer engineers, nail the basics first. Don't jump to these unless the problem really demands it.
Right, these are advanced tools for specific, constrained situations.
First up, the Bloom filter. Purpose. Approximate sets. Tests for set membership specifically. Is this item definitely not in the set? Or is this item probably in the set?
Space-efficient way to check potential existence.
Mechanism. Uses a bit array and multiple hash functions. Add an item. Hash it multiple times, set those bits to 1, check an item. Hash it, check if all corresponding bits are 1. If any are 0, it's definitely not there. If all are 1, it might be there. Could be a collision.
Allows false positive, but no false negatives.
Probabilistic nature. Can say likely in set with configurable false positive rate, or definitely not in set. Use cases. Pre-checking caches. Is this URL maybe cached? If filter says no, don't bother looking. Preventing duplicate processing. Have I seen this request ID recently? Detecting known bad IPS URLs.
Anywhere you can tolerate a small chance of a false positive to save a much more expensive operation.
Pitfalls. Only for set membership. Only useful if space is tight, otherwise use a hash set. Must tolerate false positives. Critical.
If errors are unacceptable, look elsewhere.
Next, the CountMin sketch. Purpose. Approximate counts of items in a stream. Think Bloom filters with counters instead of bits.
Estimating frequencies.
Mechanism. Similar idea, multiple hash functions, but maps to arrays of counters. See an item, hash it multiple times, increment the corresponding counters. Probabilistic nature. Can only give you an upper bound on the count. It might overestimate due to collisions, but never underestimates.
So, item X appeared at most Y times.
Use cases. Finding heavy hitters, trending topics, popular products, DDoS sources, filtering unpopular items from caches, fraud detection, ML features where approximation is okay.
Again, useful when exact counts aren't needed or are too expensive.
Pitfalls. Can't track individual items perfectly. Needs heavy space constraints. Must tolerate approximation over counting.
Not for billing or exact inventory counts.
Finally, hyperlog. Purpose. Cardinality estimation, estimating the number of unique items in a massive dataset or stream. How many distinct users visited? How many unique search terms?
Counting uniques without storing all the unique items.
Mechanism. Based on probability and hashing. Roughly, the idea is that if you hash items and see unusual patterns, like lots of leading zeros in the binary hash, it suggests you've seen many unique items. Uses multiple small registers to track these patterns, combines them for a very space-efficient estimate.
Clever statistical trick.
Yeah.
Uses tiny amounts of memory.
Use cases. Analytics dashboards, DAU estimates, unique page views, unique searches, database query planners, estimating column cardinality, cache analysis, unique keys query.
Anywhere you need a fast, cheap estimate of how many different things.
Pitfalls. Only for unique counts. Needs limited memory to be worthwhile. Must tolerate estimation errors. Standard error is typically low, like 1–2%, but it's still an estimate.
Not for situations needing perfect unique counts.
General considerations for all three. Use when memory performance constraints are severe. Your design must tolerate approximation errors. Interviewers might hint with constraints, designed for Raspberry Pi. Don't use them unnecessarily. Exact structures are easier if data is small.
What's fascinating here is how these probabilistic structures let us tackle huge problems by smartly trading precision for massive gains in memory and speed. Knowing when mostly right is good enough is a key system design skill, especially at scale. #tag cross-cutting concerns and design patterns.
Okay. As systems scale, you inevitably move from one server to many, which immediately brings up, how do you direct incoming traffic across all those machines? That's load balancing.
Essential for horizontal scaling and high availability. spreading the work.
Absolutely. In interviews, load balancing is often treated like a bit of a black box. You might just say, services are horizontally scaled behind a load balancer and leave it at that, or draw one box at the front.
Unless the interviewer specifically asks you to dive deeper into load balancing itself.
Right. There are two main types: client-side load balancing. The client itself knows about all the available back-end servers. Maybe it gets a list from a service registry or asks one server for the list of its peers.
Like Redis cluster clients or gRPC clients can do.
Benefits: no extra network hop, potentially lower latency. Drawbacks: client needs to stay updated on server health availability, can't use sophisticated balancing logic easily.
More logic complexity on the client side.
When to use: small number of controlled clients or lots of clients that tolerate slow updates, like DNS where caching delays propagation. Dedicated load balancers, the more common model. A separate server or appliance sits between clients and backends, making routing decisions.
Like AWS LLBall, Hair Proxy, Nginx.
Benefits: fast updates on server health, fine-grained control over routing algorithms. Drawbacks: adds an extra network hop, potentially adding latency.
The trade-off for centralized control and intelligence.
Dedicated load balancers perform health checks, pinging backend servers to see if they're alive and ready. And they use various load balancing algorithms: round robin, random allocation. Simple, common for stateless services, just distributes requests evenly.
Assumes requests are roughly equal cost.
Least connections, smarter. Sends new connections to the server with the fewest active connections. Good for uneven request costs or long-lived connections like WebSockets. Helps new servers ramp up too.
Tries to balance actual load better.
Load balancers also operate at different network layers. Layer 4, L4, load balancer TCP level, works with TCP connections. Fast, doesn't inspect application data, just forwards packets based on IP port. Good for high throughput, persistent connections.
Dumb, but fast packet forwarding.
Layer 7, L7, load balancer, HTTP level, understands HTTP, can inspect requests, URLs, headers, cookies to make smarter routing decisions, like path-based routing, AP orders user service, AP orders order service.
Application-aware routing. More flexible.
Can also do things like SSL termination, request response manipulation, often overlaps with API gateway functionality.
Yeah, the lines can blur between L7 load balancers and API gateways, connecting it back. Load balancing isn't just about spreading traffic, it's fundamental to resilience and scalability. The choice between client-side dedicated L4, L7 depends on your needs for latency, routing flexibility, and control. Another key architectural decision point.
All right, a crucial topic. Distributed systems fail. Servers crash, networks break, packets get lost, services slow down. It's not if, but when.
The network is unreliable. Murphy's Law applies heavily here.
Robust system design demands planning for these failures. Ignoring this is asking for trouble. Two vital strategies: timeouts and retries. Timeouts, absolutely essential. If you make a network call, you must have a timeout. Prevent requests from hanging forever, consuming resources.
Stop waiting indefinitely for a response that might never come.
Retries. If a request times out or fails due to a transient issue, retrying seems obvious. But naive retries can be dangerous.
The thundering herd problem.
Exactly. If a service is struggling and all its clients immediately retry at the same time, you just hammer it harder, potentially pushing it over the edge.
Making the problem worse, not better.
The solution: back off with jitter. This is the gold standard. Back off. Wait progressively longer between retries. Exponential back off is common. Wait ones, then twos, and fours. H-shill. Gives the struggling system breathing room.
Don't hammer it immediately. Give it time to recover.
Jitter. Randomness. Add a small random amount of time to the back-off delay. Prevents clients from retrying in synchronized waves. Instead of all retrying at 4s, some retry at 3.8s, some at 4.1s, etc. Spreads the load.
Desynchronizes the retries. Very important.
In interviews, retry with exponential back-off and jitter is the magic phrase.
Shows you understand how to retry responsibly.
Beyond single request failures, there's the nightmare of cascading failures. A problem in one service triggers failures in others, which triggers more failures, a domino effect.
Can bring down the whole system, like a chain reaction.
Imagine a database slows down. Service B times out talking to it. Retries fail. Service A times out talking to Service B. Its retries fail. Now Service A might go down. It prevents recovery.
Vicious cycle. Need a way to break the chain.
The solution: the circuit breaker pattern.
Inspired by electrical circuit breakers. Stops the flow when things go wrong.
Exactly. A software circuit breaker monitors calls to a downstream service. If the failure rate crosses a threshold, for example, 50% failures in the last minute, it trips or opens the circuit. Once open, all subsequent calls to that struggling service are immediately rejected. fail fast without even trying.
Stops hammering the downstream surface, gives it a chance to recover.
The breaker doesn't stay open forever. Periodically, it enters a half-open state, allowing a few test requests through. If they succeed, the breaker closes and normal traffic resumes. If they fail, it stays open.
Self-healing mechanism.
Benefits: fail fast, better UX than hanging, reduce load on failing services, enable self-healing, prevent system-wide outages, great for external API calls, DB connections, any service-to-service call.
This really gets to the heart of building resilient systems. Systems that not only withstand failures but can heal themselves. Circuit breakers are proactive resilience, stopping localized problems from becoming catastrophes. Building in self-preservation, #, identifying common system design patterns.
What's really interesting about system design is that while every problem feels unique at first, the solutions often involve combining established, well-understood patterns.
Yeah, recognizing the underlying pattern is key. It's like having a playbook.
It saves you from reinventing the wheel, often badly, helps you build scalable, robust architectures more reliably. One fundamental problem that comes up constantly is dealing with contention. Multiple users trying to access or modify the same resource at the same time.
The last concert ticket, the auction bid, editing the same document.
Right. Leads to race conditions, inconsistent data if not handled properly. Solutions vary. At the database level, you might use pessimistic locking, blocking others, or optimistic concurrency control, checking for conflicts before commit.
Letting the database handle the concurrency control.
In distributed systems where data might be spread out, it gets harder. You might need distributed locks, using Redis, Zookeeper, two-phase commit protocols, or maybe queue-based serialization, forcing operations into a single line.
More complex mechanisms needed when the DB can't handle it alone.
Key takeaway: understand when atomic operations transactions are enough versus when you need explicit locking. Databases are designed for contention. Breaking data across multiple DBs often reintroduces contention problems you then have to solve manually. Be careful about premature sharding.
Yeah, sharding solves some problems but creates others, like distribute consistency.
Beyond contention, many other patterns keep reappearing, often linking back to things we've discussed. Handling large blobs. We covered this use object storage.
Right, metadata in DB, blob in S3 GCS.
Managing long-running tasks. Video transcoding, report generation often involves queues like Kafka or RabbitMQ for asynchronous processing.
Decouple the request from the long-running work.
Real-time updates, notifications, live data. Typically uses WebSockets, server-sent events, SSE, or PubSub, often via Redis.
Pushing data to clients proactively.
Multi-step processes, complex workflows, often coordinated by queue streams or dedicated job schedulers orchestration tools.
Managing state across multiple asynchronous steps.
The skill is recognizing which pattern fits the problem and understanding its trade-offs. Start simple, polling, single server orchestration, and only add complexity when requirements demand it.
Yeah, don't over-engineer. But knowing the patterns helps you choose the right simple approach or scale effectively when needed. What's fascinating here, as you said, is that mature system design is about pattern recognition. Knowing the components is one thing, but applying these battle-tested patterns to common problems. That's how you build architectures that are functional, resilient, performant, and maintainable. Standing on the shoulders of giants, really. Hashtag tag outro.
Wow, okay, what a journey. We really covered a lot of ground there. From the absolute foundations like CFP theorem and the mysteries of networking.
The stuff happening under the hood.
All the way through API design choices, the role of API gateways, the strengths of relational databases like Postgres, the scale you get from NoSQL like DynamoDB and Cassandra.
Handling different data shapes and scales.
Then object storage for blobs, consistent hashing for distribution, Kafka for reliable messaging, Redis for that in-memory speed, Elasticsearch for powerful search.
Even those approximate data structures for when close enough is required at massive scale.
And wrapping up with load balancing, handling failures gracefully with timeouts, retries, circuit breakers, all viewed through the lens of common design patterns.
Phew. Yeah, that was quite the tour.
Every single piece we've discussed today, from the why to the how, is really a fundamental building block for pretty much any modern distributed system.
They don't exist in isolation either. They all interact, influence each other.
Exactly. They interconnect to form these robust, scalable architectures that power, well, everything around us online. We truly hope this deep dive has served as a kind of foundational audiobook chapter for you.
Helping you not just understand the concepts, but see how they fit together into a cohesive whole.
hopefully preparing you to really master system design.
And connecting it all back. The real goal here isn't just memorization, right? It's about making informed choices. Every decision, consistency versus availability, data structure choice, messaging paradigm has profound implications.
Hmm. Performance, resilience, cost.
Exactly.
Yeah.
So as you move forward, maybe think about an everyday app you use. Can you start to spot the CIP theorem trade-offs it must be making? Can you guess which data structures or patterns might be powering its features?
That's a great exercise.
Once you start seeing the world through this lens of system design, honestly, every application becomes this fascinating puzzle just waiting to be understood.
Absolutely. It really is like gaining a superpower to see the architecture behind the curtain.
Hmm.
Well, thank you so much for joining us on this very deep dive. We're excited for you to continue your learning journey.
Keep exploring, keep questioning.
And we'll be here with more insights, more details, and hopefully just enough terrible analogies to keep you hooked on our next deep dive.